So yes, well, being the Austin Center and having supercomputing in your hometown, which, by the way, if any of you are considering doing that, it's a horrible idea. I would like to recommend against it at this time. Somebody said at the opening that thanks for coming when supercomputing starts tomorrow. Supercomputing started conservatively last Wednesday. And I know all of you know this, so we have other meetings to get to. So let me just add my welcome to Austin on behalf of TACC. You're actually just a few miles from our center. If any of you would like to come by and visit, many of you have been there before, just looking around the room. But well, one, you can come see us on the floor. We have, it being near home, 30 talks, papers, BOFs, and tutorials. But we're also running tours up by bus. I think there's a special DDN bus one day, and 14 other buses that are coming. We're trying to keep the head count at the center just under 1,000 for this week, but come on by. You can sign up at our booth starting tonight if you'd like to see things. There's a number of DDN platforms that you can see, among many other things, like all the stuff they're attached to. SC being a practitioner's meeting, I needed to do just a little bit of a plug. So one thing that we're sort of focusing this year is we've built a ton of software tools for people who actually run clusters and run supercomputers and storage systems of various kinds. And these are the ones that haven't happened yet. Many of them were yesterday and the day before. So, and I'm sure the slides are available somewhere, so you can come see all those. So before I dive into the thesis for today, and apologies to those of you, this is already my 5th supercomputing talk, so you might have seen this next few slides before, but let me just give you a quick rundown of our center and what we do. We build big machines. I have to keep showing this slide until whenever Jack releases the top 500 list in the morning, because we're still number 8 right now, and we probably won't be tomorrow, so, oh, it's out now? Yeah, well, okay, so. Well, I submitted the slides yesterday, so it was accurate at the time. So, but apparently number 10 in the world now. We've built a number of large-scale computing platforms, and with that comes a number of storage. What we're most proud of about them is that not only do we build a lot of platforms, a lot of people use them. So Stampede, which is now down to number 10 from number 6, but is 3 years old. It's its 6th list, so that's not too bad to fall to number 10 on your 6th time on the list. Maybe 7th. I've lost track. But it's been remarkably successful. We've done more than 2 billion hours of user jobs, 6 million different user jobs, 2,500 projects on our system. Somewhere around 10,000 people have logged in directly and run a job through a production queue on it. Somewhere between 35 and 50,000, it's hard to pull out overlap in the big user communities, have come through the web portals and use it. And even though it's a 3-plus-year-old system at this point, we have, for the 180 million hours we have available for the quarter starting in December, we have 1.2 billion hours in requests for time on it. So it remains wildly popular in terms of who wants to use it. So those are things that probably just about everybody who comes to supercomputing, I would hope, knows about TACC, is that we have a lot of big systems. We also use really small fonts. Apologies for that. I didn't realize the slide was going to come out quite that small. Welcome to the conversion to 16 by 9 slides everywhere. But so things you may not know about TACC, right? Stampede is our big platform and our core HPC platform. But as we start thinking about where and how we need to store data, we actually have 15 different public platforms, some of which are HPC, some of which are focused on machine learning, data-intensive computing, cloud, visualization, interactive, and so on and so forth. We have lots of different kinds of systems we build now. So that's more about divergence. This talk will be about convergence. We also hold an enormous amount of data in a lot of different forms, right? The old HPC mode of using data was Scratch. At this point, in addition to things like Scratch, we have about 200 public data collections that we curate for folks one way or another that are long-term, permanent, usually web shared, occasionally SQL shared or something like that. But lots and lots of data across the center. We have about 3 billion files and 50 petabytes at this point in various forms of storage. More about that later. We mostly develop software at this point. We maintain about 30 web portals, again, some of which have 35,000 plus users. I don't know the exact number of how many web users we have, because if you have 35,000 in one genomics portal and 30,000 in another life sciences portal, odds are they're mostly the same people, but it's hard to tell. So federated identity is another talk. We actually now have systems for actual computing science development, as opposed to computational science. So just this year, we put up systems that users can have root on, because fortunately, there's now the bare metal cloud software stacks, which remove the last vestiges of cybersecurity from the world when you give users root access to your systems. So yeah, what can go wrong? At the same time, if you're going to roll out systems that users have root on, you might as well up the compliance game too, right? So we've also added HIPAA and FISMA and FERPA certifications this year up to FISMA moderate data because we're actually holding a lot more sensitive data while giving users a lot more access. So those may be the less well-known things about TACC. Just a little bit about the center itself, the sort of org chart size. We're at about 160 folks, 135 full-time people. We have 26 students as of right this minute. So around 160. I like to say we're a consulting firm near UT because we get about 10% of our money from UT and we're 85 to 90% externally funded. We have some big data centers you can come see. We're up around 12 megawatts of facilities. And growing and growing. But that's not really the interesting way to slice up and talk about the center. I think of it in sort of three categories. We have the systems part, which is what people mostly want to hear about here, but the compute and the data systems that provide the foundation for a real technical ecosystem for doing science and engineering work. On top of that, we have sort of our community cyber infrastructure because the systems are a very small fraction, as I'll go into, because there's a big I almost said big data by accident. There's a very large story related to data in that particular world, but community-specific support is crucially important to actually getting work done. And then we have a lot of development projects and sort of building the future cyber infrastructure. And we do some cool stuff with it. The poster on this in the booth is called It Actually Is Rocket Science. But we have designed some jet engines this year with our partner Firefly, or Rocket Engines. That's the new Firefly launch vehicle, which will launch in 2018 to do microsatellites and satellites up to 400 kilograms. That was the launch platform in Cedar Park, Texas, which is maybe 25 miles north of here. That was the first engine test. It was about 4 weeks ago. So they've started firing off the rockets. And all the simulation for that was done on Stampede. We do the basic science. This is the turbulent flow for plasma infusion with folks at Princeton. We do evolution work in life sciences like all the other big centers. This one got the cover of Nature this year. So lots of good science highlights. And we have a lot of DDN platforms as well, including one that's sort of at the center of our ecosystem, but that's a couple of the larger ones. There's a few more. Corral is one of our older ones. We're about to deploy Corral 3 in 2016, so we've had that for 7.5 years or so, Tommy, at this point. We've had versions of Corral. The current incarnation is 12Ks, SFA 12Ks, 10Ks, right, that's why it's about to be upgraded. But this is where it's actually mirrored between the data center here and one up in Dallas, and it's where we manage all those public data collections and any other shared data where we're worried about curation and access outside of our HPC platforms, sort of broadly sharing data with the world, and that's been done in partnership with DDN. Stockyard is a totally different use case, also taken with better lighting. That's the one on 12Ks. That's our global work file system, sort of that interim level between home and scratch. Semi-persistent data and also data that migrates from system to system, as a lot of the other big system centers have, where we try and persist between generations of Stampede. And it supports things, not only the ability to use the unique qualities of each one of our systems, right? If you want to do simulation on Stampede and visualization on Maverick, it's an easy way to do that because you don't have to do any actual data migration versus a cloud. It's also great just for migrating between generations of systems, right? When we went from Ranger to Stampede 3 years ago, before we had Stockyard, just copying all the data took 2 months. We had to stand up both file systems and let users loose on it. As you know, there was petabytes to move and billions of files, and it's a long-running process, and if you let users do it themselves, it's even worse. So, but we also do, through DDN, all of the scratch storage on our Lone Star 4 and Lone Star 5 platforms, and our newest platform, Hikari, which is a water-cooled Apollo 8000 with some solar panel that runs on 380 volts DC that'll get announced at the HP booth at 7:30. So if you're not doing anything later, talk number 6. That's sort of where we are today, what we're doing with DDN. I swear I'm going to stay on time. So let me just go back in time about a little bit and then talk about where we are in data. And again, apologies to those of you who've seen me give this particular set of slides before, but that was my first cluster actually it was second cluster. My first x86 cluster circa 1992. One of the very early Beowulf machines. We got a lot of support from the system integrators. We ordered parts out of the back of Computer Shopper. I remember laminating the shelves for the cabinet there in my boss's garage. Highly integrated, right? Do-it-yourself clusters, grad students, in this case me, run the systems. And you just figure out that users are going to figure it out, right? You give them a login. The time, this was actually pre-MPI, so you kick them out with a PVM library, and you figure out, they're smart people, they're physicists, that'll probably work out. We figured out that wasn't the case, right? We've matured greatly in our approach to how we build things today, right? Our systems have grown up a lot. Our software approach, our user support, all of that has grown up a lot over the years. And now we're seeing perhaps a similar thing with data, largely because the center has had to evolve to deal with all of these new use cases that we see. So that way. So if you look at our center, a little more than half a decade ago, we sort of had 3 groups. We have 11 now. And it's not just scale. It's not the 3rd Brigade. We have new kinds of expertise that we have. But we'd sort of, build platforms to do big, mostly PDE-based simulation. Right, we'd had a viz group, and then you have people to actually help them run it, because it turns out if you just give them an MPI library, they don't really get that far. But we've evolved a lot, and sort of trends and pressure. Again, this slide is another one that I've shown a lot, but tons and tons of new kinds of users, right? We have as many users requesting time in computational economics as we did in computational physics 12 years ago, right? Just enormous growth in that. Life sciences has been even bigger growth, and we have more use cases in life sciences than I can count. And most of those are driven by MDs, so what can go wrong there? The things that most of these new users have in common, right, is no longer are we doing PDEs, we're doing statistical models, all driven by data, mostly non-programmers, mostly less traditional languages, and some other requirements that I'm going to talk about in a minute. No performance tuning at all. As I mentioned, much of the work in cyber infrastructure today is beyond the systems level, right? The way that we interact with the user community is not just standing up a platform and giving an SSH account, right? We often interact by building the user interface, by building the data management, really a customized community cyber infrastructure approach. And these are a few of the ones in immunology and plant science, and now in earthquake, wind, and flood hazard engineering, that we've built these sort of large communities. And the majority of our staff do software work at this point, a lot of it in this. We have, I have 25 web developers and API folks, right? We had 0 of those 5 years ago. So a huge number. And if you look across these projects at the needs, sure, they still need computing and analysis more than they think they do, and most of the times. And yeah, they store a whole lot of data. There's enormous volume and growth in the data there. But I've sat through, 150 days of requirements meetings in the last 10 years, from ocean metagenomics to civil engineering. And what people largely talk about, and where most of the effort is in data integration, right? We have very disparate types of data, and we don't know how to make them all work together. In data curation and in versioning and in replication, how do we reproduce the science that we're doing? How can we get that copy of the database that we had a year ago that we ran this analysis on that's not the one today, right? Well-known problem. Data sharing and collaboration is huge. Right now I have a version set of the data. I need to get that one to my colleagues and attach it to my publication. And the big one is actually data quality and cleaning and verification, right? Data's noisy, data sucks. You find lots of problems in it. You need to make it better. And then there's a fair amount of actually moving that data around, right? So we've had to think, if this is what our users want, how do we change what we do? A few other things. We have like 15 platforms now, as I mentioned. Most of the users who are coming in at that web level don't care. Then we have 15 platforms, or what the differences is, or how they're customized, right? So they want to see us as a service, primarily, and that's sort of trite to use the as a service thing. Platform as a service, infrastructure as a service, and so on at this point. But frankly, they want, they don't care about maintenance times or anything else. They want to submit jobs from the portal, or data queries or whatever it is, and just have them work. So they, perhaps if it's an external developer building the portal, they see our APIs, but they never see a system maintenance banner. So for us, it's less hardware details, less systems, more services, and of course, in this area of less sophisticated and much wider range of users, you get some software stacks that are just scarily bad. So, and we have a lot of them. So guiding our approach, right, we have about 3,000 projects. I mentioned how many users we have. We do tons of profiling. We know everything that runs on the systems. We know 34 codes cover about half of our cycles, and we know 4,000 codes cover the other half. So again, fixing all the codes or having them work in a particular way isn't an option. We also know we're moving a lot of data. At last count, we're moving about 3 petabytes a month in each direction, in and out of the center, more than a petabyte through REST APIs. The scary part of that is the amount we moved through REST APIs last January was 100 terabytes, and the amount the January before that was about 5 terabytes, which makes Moore's Law look pedestrian if you look at the growth rate and how much data we're moving in and out. And then finally, a lot of these users do a ton of analytics. So in HPC terms, short jobs, and short jobs with small I/O. The exact opposite of what we spent 30 years getting ready to do. It is not exascale, right? It is 4K or 512 byte IOs in massive numbers and jobs that they want to turn around in 10 or 15 minutes, right? A very different use case than we're used to, right? So they want interactive, for instance. Graph databases, Hadoop, Spark, all these things. Really small random reads. Good to see progress on that in some of the slides, but not large coordinated MPI I/O. So our traditional file systems are not exactly ideal for that. In fact, our HDFS approach is to not use Lustre, just separate it. So what do we do with 3 minutes to go? So one is, the divergent part of what we do is we've built a lot of different systems to meet these different needs. And so we've architected a system mostly based around Flash to do very small IOs and to run stuff that we don't want to run on our production Lustre file systems, and to run stuff that we don't want to run through our batch queues that are tuned towards large jobs. But then we have to glue all that stuff together, and this is the convergent part. So we do shared storage across all the platforms with Stockyard. So users don't have to move their data to run very complicated workflows, which I think gives us a huge advantage over the commercial clouds. Because, S3 is a great platform. Try computing on it, and then try computing 5 different places on it, checking in and out each time. It's enormously expensive, not only in time, but in dollars. And you have to stage somewhere faster to do real work. We've also put APIs across everything that we do and standardize. And so that's a place where points to the commercial cloud for coming up with that, even if everybody gets to pick their own standard and change it all the time. And 3, we also have the different kinds of storage we need. So we have glue storage, but we don't just have one tier of glue storage. We have object storage, we have file storage, increasingly we have HDFS storage, and then we have archive across the different tiers. So Wrangler is our fast analytics platform. It's a big shared flask. Corral is our data management platform. Stockyard is sort of our staging and sharing platform. Ranch is our archive platform. Rustler is our object store platform. So we've had to build all of these kinds of storage, but we share them everywhere. So when we think about all the kinds of computing in our ecosystem, we have high performance, interactive, data intensive, cloud, et cetera, but what glues them all together is the shared storage. And that's really the story is at this point, and that happens to be DDN, and it goes in the heart of our, this is not really the architecture figure I'm supposed to be showing, the graphics people would be horrified, but it's the one about how we organize internally and think about it is put storage at the center of what we do and build out from there so we can do really cool stuff like build rocket engines, do wave tank simulations, all of which you can come see at the booth, simulate the universe, store data about strokes, et cetera, and change the world. So 25 seconds to go. So I can maybe even take a question, but thanks. So.